In previous videos, we talked about the gradient descent algorithm, and we talked about the linear regression model and the squared error cost function. In this video, we're going to put together gradient descent with our cost function, and that will give us an algorithm for linear regression, for fitting a straight line to our data. So this was what we worked out in the previous videos. There's our gradient descent algorithm, which should be familiar. And here's the linear regression model with our linear hypothesis and our squared error cost function. What we're going to do is apply gradient descent to minimize our squared error cost function. Now, in order to apply gradient descent, in order to write this piece of code, the key term we need is this derivative term over here. So we need to figure out what is this partial derivative term, and plugging in the definition of the cost function j, this turns out to be this, sum from I equals 1 through m of this squared error cost function term. And all I did here was I just plugged in the definition of the cost function there. And simplifying a little bit more, this turns out to be equal to this, sum from I equals 1 through m of theta 0 plus theta 1 xi minus yi squared. And all I did there was I took the definition for my hypothesis and plugged it in there. And turns out we need to figure out what is this partial derivative for two cases, for j equals 0 and for j equals 1. So we want to figure out what is this partial derivative for both the theta 0 case and the theta 1 case. And I'm just going to write out the answers. It turns out this first term is simplifies to 1 over m sum from over my training set of just that, xi minus yi. And for this term, partial derivative with respect to theta 1, it turns out I get this term, minus yi times xi. Okay? And computing these partial derivatives, sort of, going from this equation, right, going from this equation to either of the equations down there, computing those partial derivative terms requires some multivariate calculus. If you know calculus, feel free to work through the derivations yourself and check that if you take the derivatives, you actually get the answers that I got. But if you are less familiar with calculus, don't worry about it, and it's fine to just take these equations that were worked out, and you won't need to know calculus or anything like that in order to do the homework or to implement gradient descent and get that to work. But so armed with these definitions, or armed with what we worked out to be the derivatives, which is really just the slope of the cost function j, we can now plug them back into our gradient descent algorithm. So here's gradient descent for linear regression. We're just going to repeat until convergence. Theta 0 and theta 1 get updated as this thing minus alpha times the derivative term. So this term here. So here's our linear regression algorithm. This first term here, that term is, of course, just the partial derivative with respect to theta 0 that we worked out on the previous slide. And this second term here, that term is just the partial derivative with respect to theta 1 that we worked out on the previous slide. And just as a quick reminder, you must, when implementing gradient descent, there's actually this detail that you should be implementing it so the update theta 0 and theta 1 simultaneously. So let's see how gradient descent works. One of the issues we saw with gradient descent is that it can be susceptible to local optima. So when I first explained gradient descent, I showed you this picture of it, going downhill on the surface, and we saw how, depending on where you initialize it, you can end up at different local optima. You end up, here or here. But it turns out that the cost function for linear regression is always going to be a bow-shaped function like this. The technical term for this is that this is called a convex function. And I'm not going to give the formal definition for what is a convex function, C-O-N-V-E-X, but informally, a convex function means a bowl-shaped function, you know, kind of like a bowl-shaped. And so this function doesn't have any local optima except for the one global optimum. And does gradient descent on this type of cost function, which you get whenever you're using linear regression, it will always converge to the global optimum because there are no other local optima other than the global optimum. So now let's see this algorithm in action. As usual, here are plots of the hypothesis function and of my cost function j. And so let's say I've initialized my parameters at this value. You know, let's say usually you initialize your parameters at 0, 0, theta 0, and theta equals 0. But for illustration, in this particular implementation of gradient descent, I've initialized, you know, theta 0 at about 900 and theta 1 at about minus 0.1. Okay, and so this corresponds to h of x equals, you know, minus 900 minus 0.1x is this line. And so out here on the cost function. Now, if we take one step of gradient descent, we end up going from this point out here, a little bit to the down and left, to that second point over there. And you notice that my line changed a little bit. And as I take another step of gradient descent, my line on the left will change, right? And I've also moved to a new point on my cost function. And as I take further steps of gradient descent, I'm going down in cost, right? So my parameters is sort of following this trajectory. And if you look on the left, this corresponds to hypotheses that, you know, seem to be getting to be better and better fits to the data until eventually I've now wound up at the global minimum, and this global minimum corresponds to this hypothesis, which gives me a good fit to the data. And so that's gradient descent, and we've just run it and gotten a good fit to my data set of housing prices, and you can now use it to predict, you know, if your friend has a house that costs of size 1250 square feet, you can now read off the value and tell them that, I don't know, maybe they can get $250,000 for their house. Finally, just to give this another name, it turns out that the algorithm that we just went over is sometimes called batch gradient descent. And it turns out in machine learning, I don't know, I feel like us machine learning people, we're not always great at giving names to our algorithms. But the term batch gradient descent means that refers to the fact that in every step of gradient descent, we're looking at all of the training examples. So in gradient descent, you know, when computing derivatives, we're computing these sums, right? This sum of. So in every step of gradient descent, we end up computing something like this that sums over all m training examples. And so the term batch gradient descent refers to the fact that we're looking at the entire batch of training examples. And again, this is really maybe not a great name, but this is what machine learning people call it. And it turns out that there are sometimes other versions of gradient descent that are not batch versions, but that instead do not look at the entire training set, but look at small subsets of the training set at a time. And we'll talk about those versions later in this course as well. But for now, using the algorithm you just learned about, or using batch gradient descent, you now know how to implement gradient descent for linear regression. So that's linear regression with gradient descent. If you've seen advanced linear algebra before, so some of you may have taken a class in advanced linear algebra, you might know that there exists a solution for numerically solving for the minimum of the cost function j without needing to use an iterative algorithm like gradient descent. Later in this course, we'll talk about that method as well, that just solves for the minimum of the cost function j without needing just multiple steps of gradient descent. That other method is called the normal equations method. But in case you've heard of that method, it turns out that gradient descent will scale better to larger data sets than that normal equation method. And now that we know about gradient descent, we'll be able to use it in lots of different contexts, and we'll use it in lots of different machine learning problems as well. So congrats on learning about your first machine learning algorithm. We'll later have exercises in which we'll ask you to implement gradient descent and hopefully see these algorithms work for yourselves. But before that, I first want to tell you in the next set of videos, I first want to tell you about a generalization of the gradient descent algorithm that will make it much more powerful. And I guess I'll tell you about that in the next video.